Okay, great. Hi, everyone. Again, I'm Sam. I just want to thank Martin and the Next Build team for having me here today. There's been some great lectures, so I hope to follow up on that with my lecture. And so to start, I would say I am a member of the Cluster of Excellence on Integrative Computational Design and Construction for Architecture, otherwise known as the NCDC. The NCDC is a research cluster composed of various institutes across different disciplines from the University of Stuttgart, the Max Planck Department on Intelligent Systems, and recently the Technical University of Berlin. And one of those institutes is actually the one that I am from, which is called the Institute for Computational Design and Construction. And as you might have guessed from the name of our cluster, our main focus is research on the topics of architecture and construction. And more specifically, we aim to develop fundamental computational design methods based on continuous and multidirectional feedback between the various facets of architecture. And so what does that mean? We are developing computational design and engineering methods, cyber-physical robotic fabrication and construction processes, effective digital material and building systems, and we are reflecting on that from the perspectives of environmental, sociocultural, and ethical perspectives. And why we do this, you might ask, and I think probably we've discussed this a bit today. Well, architecture has huge economic, ecological, and sociocultural relevance for our current society, but the United Nations Status Report in 2017 also reported that in the next 30 years, our built world will need to be built again in order to meet the needs of rapid urbanization and, of course, population growth. And if that sounds crazy, it actually is, because our current means of architectural construction are not capable of doing this. And one of the major reasons behind that actually is the digitalization in the construction industry. As you can tell from this graph here, construction, as compared to some other industries, is really not so digitalized. And one of the major obstacles we postulate as a cluster is that in architecture, there's a separation between the design and engineering of a building from its fabrication and construction. And this has led to efforts of digitalization to be conducted at a discipline basis. As such, recent approaches to the integration are focused on linear transformation of progressively more detailed models from one phase of a building to a next. And that is why we propose, or we believe, that our integrative design approach based on feedback between the various disciplines has the possibility to unleash the full potential of digital technologies for architectural construction. This includes specific attention to fabrication and construction of buildings, which to date, if we look at modern construction sites, happens mostly with manual processes. So in the first phase of research at the NCDC, which is about to wrap up this month, we've looked at the automation of construction at different scales using different machines in different contexts. So at the largest end of the spectrum, we've been working on the full automation of a tower crane to realize pick and place for the construction of multi-story buildings. Similarly, we are using existing construction equipment to develop cyber-physical fabrication platforms, in this case using a spider crane. Further research is interested in the creation of fabrication platforms which could fit on the back of a truck and be transported from a factory setting on site using industrial robotic arms for the prefabrication of building components out of wood or fiber. And at the smallest end of the spectrum, we are interested in or researching distributed robotic systems that are capable of building structures that are much larger than the machines themselves. And the picture that you see here is a project that I'm going to focus the rest of the presentation on, and what I've been developing with some of my colleagues together at the NCDC. And before I go into detail, I think it's important to understand what distributed robotics actually is. And to do that, I generally like to show these images because they are robots that are fairly well known and similar to the ones that I'm interested in. They are mobile machines, which are relatively small, fairly cheap, easily transportable, and able to move in their environments. And as the technology for deploying such machines is becoming more robust, they're starting to revolutionize our everyday lives. So here you see, of course, vacuuming our apartments, and although maybe only tested so far, delivering packages from manufacturer or provider and consumer. And when we combine these machines together, we get distributed robotics. So distributed robotics is a term to refer to teams of mobile robots that work together to solve complex tasks through their shared intelligence and their robotic capabilities. Compared to other forms of automation, these systems have the potential to boost overall flexibility in their mobile nature, increase fault tolerance that if one machine dies, another one can take its place, and reduce costs as the machines themselves are relatively inexpensive. And in recent years, because of these advantages, we've seen distributed robotic systems more and more in research with people investigating how such machines could build structures on construction sites. And these systems potentially have the possibility to break from other conventions in construction due to their ability to quickly adapt to site-specific conditions, respond to different architectural use cases on the fly, and work at potentially unlimited scales. However, the field is pretty young and fairly complex due to its interdisciplinarity. So the majority of research is focused on, so far, simple structures with non-conventional materials, and often leaves real architectural constraints kind of to the side. So noticing that, I began research developing distributed robotic systems that are specific to architectural construction, starting with my master's thesis at the University of Stuttgart in the ITEX master program with Ramon Weber. And this now has become a part of the NCDC and two other institutes, the Max Planck's Physical Intelligence Department and the Technical University of Berlin's Learning and Intelligence Systems Lab have joined me to work on a project entitled Leveraging the Building Material as part of the robotic kinematic system for parallel construction. And we are using the NCDC approach of co-design in order to co-optimize and co-develop a distributed robotic system specifically for timber construction. More specifically, we are working on the overall system development, so this includes artifact design ranges, material specification, and construction strategies, methods for artifact design using agent-based modeling, and approaches for task and motion planning, so planning how the robots move using logic geometric programming. And we're also developing the physical hardware with a digital twin propagated by a visual tracking system for the assembly of real structures. So then the system we are developing is actually, which you've seen in some of the imagery so far, is composed of a timber strut and a robotic actuator. The actuator has the ability to rotate, grip, and communicate. And using these abilities, the actuators can combine with the timber struts in order to form robot material kinematic chains. Kinematic chains are similar to industrial robotic arms, composed of links and joints, but can further break apart during the construction process to form kinematic chains of varying degrees of freedom. So the robotic actuators must leverage the timber struts for the entire construction process. A single robot is not able to move on its own, so it's the combination and interaction of the two elements in forming, breaking, and adapting the kinematic chains that allow for the movement of the robots, the manipulation of the material, and then eventually the assembly of an artifact. This, however, poses a major challenge for the hardware, as the robotic actuator needs to be able to occupy any position in the kinematic chain. This is demonstrated when we look at an industrial robotic arm, as the first axis is generally quite large. And although we can possibly conceptualize our robotic actuator with such a large motor, it might prevent the whole system from being fairly lightweight and highly mobile, which are important for its ability to climb on and within the structure that it constructs. So we approach this challenge through the analysis of locomotion and manipulation capabilities of different kinematic chain topologies. And again, the benefit of the system here is that we can break down the system. We don't need to work with 6 axes in a single kinematic chain, but can work with as little as a single axis. And through this analysis, we learn that it's possible to assemble structures in plane with kinematic chains with only 2 degrees of freedom. So this is achieved through something like you see on the screen here, and I showed already once, where the kinematic chains first locomote to a strut that's provided into the environment, here marked in green, and then collaborate, walking over a fixed bed of struts, and then passing the strut along the edge of the structure in order to kind of continue the construction process. So the prototype we are developing is based on exactly this, kinematic chains, which form between 2 robots and 1 timber strut. Taking a closer look, the robotic actuator is composed of 2 opposite-facing grippers, separated by a slewing ring, a rotational mechanism that allows it to rotate 360 degrees. And those work together with a strut of dimension 50 by 50 millimeters with a milled groove that you can see there. The reason why we introduced this level of co-design between the gripper and the timber strut is to help deal with the heterogeneous nature of timber material. The geometry of the gripper paddle meets with the timber strut in order to help align the timber struts to the correct position and orientation. Another important feature of the robot is its ability to lift the timber in order to avoid friction with the plane on which is a building. This is achieved through a spring loading the gripper. So first, the robotic actuator is able to close its gripper arms in order to grasp the material, and then through further actuation, pulls the material closer to the robotic body. In order to test the robotic actuator and prove that it would be capable of such a process like this, we designed a series of experiments. The experiments aimed at showcasing 3 tasks necessary for construction, which are listed on this screen here: locomotion, dynamic kinematic chaining, and transportation. And the experiments further use an increasing amount of robotic actuators, 2 for locomotion, 3 for dynamic kinematic chaining, and 4 for transportation, to showcase that the ability of the system changes with the amount of robotic actuators that are present. So the details of these I will quickly explain right now. The task of locomotion involves 1 kinematic chain locomoting or moving itself across a bed of fixed struts. This is accomplished through the 2 robotic actuators performing a series of grips and ungrips, again, on the bed of fixed struts that you see there. Dynamic kinematic chaining builds upon locomotion by introducing the dynamic nature of the system that is inherent to its modularity. So for this task, 3 robots are fixed or gripped to the struts. The first robot passes the strut to the second and third build a kinematic chain and are able to locomote to a new location. And this is mainly, could be useful for changing the length in between robots or potentially picking up robots that are left on the structure somewhere. Transportation is the final assembly task and involves the passing and placement of timber struts. So here for robots, as you can see, they first pick up the strut on the left side and then pass it over to the right. And these, if we combine these tasks, we can consecutively build up the layers of structures like the ones that you see on the screen. We further tested the system in environments of randomized struts and in the vertical plane, and as such we can start to validate or think about that these teams of robots can work in parallel at the same time on a structure, but potentially in different planes in order to be able to assemble more complex building artifacts. And so one of my specific interests in the research team is exactly on this question of design, more specifically on design methods and interfaces for designing and potentially rearranging architectural artifacts built by the distributed robotic system. This includes both top-down methods in which designers develop blueprints that the robots have to execute, and bottom-up methods in which the design emerges from the construction process itself. And currently, I'm doing that through the creation of agent-based models, which colleagues of mine at the ICD are developing in different contexts. For those of you who might not be familiar, agent-based modeling is a computational approach that aims at understanding complex systems through the simulation of interactions between agents in an environment. The classic example of this being the simulation of the flocking of birds. And ABM is interesting, or agent-based modeling is interesting to us because it's able to handle the complexity of architecture and construction, and more specifically, integrate different perspectives or parameters, constraints from the different disciplines in the AEC industry. ABM also allows us or allows for the emergence of designs that would otherwise be quite difficult for us to imagine. Of course, some have more architectural relevance than others. And the research that I am doing on distributed robotics and agent-based modeling is contributing to our in-house ABMX framework. The goal of the framework is to provide an open code base in C# and Python for researchers and professionals in the AEC to develop agent-based models, which we are hoping to release in the upcoming months. And therefore, my addition to the framework would be to help in the generation of models specifically for distributed robotics. And when starting the process of creating such a model, initial interesting question is, what does the robot actually represent? So in this case, it could be the building material itself that the robots are assembling, or the robots. And this has direct implications on the overall setup of the model, including how the environment is represented, as well as the definition of the behaviors that control the actions of the agents. And because both of those approaches are actually viable and interesting, I've been systematically investigating both. So on the left, you see a model in which the agent represents building material, and on the right, an abstraction of the kinematic chain. And this investigation has led to questions of how much a designer really needs to be involved in the process, how much control should the robots have, how do you express design intent as a designer to the robots, which has then brought back the question of the whole design process. So coming back to these images that I introduced earlier in the presentation, when the agent represents building material, the design process is decoupled from its planning. Therefore, the entire process is similar in that the design, planning, and construction phases of a building are explicitly delineated, as you see on the left. And when we define an agent as the mobile robot, the planning required to achieve a design is determined in parallel to the design itself. And as such, the construction phase of a structure, as well as potential adjustments or its deconstruction, can be considered in the same model. In order to test these design processes and wrap up our first phase of research in the cluster, again, which is coming to an end this month, we started a larger scale demonstration in our large-scale construction robotics laboratory just outside of Stuttgart at the beginning of this month. So we plan to use the 4 actuators here in order to build a slab-like structure on top of this plate, so build up a couple of layers. Unfortunately, we're not as far along as I wanted to be for this presentation today, so I can only give some first impressions, but I think it will give an indication of what is kind of possible here. So the overall workflow for this demonstration is explained here. There's constant feedback between a digital twin that is composed of the agent-based model for design, the task and motion planner, and the perception algorithm, and this has constant feedback to the physical system, which includes, again, the timber struts, the robotic actuators, as well as the external vision system. And the process begins with a designer defining design intent using the digital twin. This is this design intent, which includes configurations of the struts and robots, is sent to the task and motion planner. The task and motion planner is being developed by our colleagues at the Technical University of Berlin. Through the task and motion planner develops a plan that's sent to the physical system for execution. The execution is then monitored by the external tracking system, which at the end of its execution can update the digital model, and the process can run iteratively in order to update the digital twin and adjust for any tolerances in the system. So this is a screenshot from what we have developed, or a screenshot of the interface that we have developed for the workflow. It allows us to design, plan, communicate instructions, and monitor the entire process. The blue represents the real robots, and the pink is the planned motions. In moments like the ones that you see on the screen here, adjustments of the actuators occur. Like when a kinematic chain is attempting to change its gripper state, the visual tracking system kicks in. And so that's why you saw in some of the videos, and you will see here, that the whole process slightly slows down right before and after the robot grips, because that's when, again, the tracking system is kicking in. We also plan to test our connection strategy in this larger assembly. I'd previously designed an effector which would allow the robotic actuator to screw timber struts together. This is consistent of some custom parts surrounding an automatic screw feeder, which allows the robot to carry along with it a couple of screws and then perform multiple connections. So this was the first prototype, which was working fairly successfully. Now we're working on increasing its stiffness and decreasing the amount of time it takes in the next generation for the new robot. And with that final demonstration, we hope to further validate at a longer horizon the ability of distributed robotic systems to build structures. Due to the flexibility of this system in particular, struts can be placed at varying densities and at different orientations on a continuous plane, leading to building artifacts that are much larger or even more complex than, well, depending on how you look at it, than a single robot or a strut on its own. In the next phase of the NCDC, which will continue for another 3.5 years, we plan to build upon this research, breaking away from two-dimensional building artifacts into three-dimensional structures. We hope to continue to conceptualize a future or construction future where mobile machines can robotically build or adaptively change structures on site. So to wrap up and zooming back out a bit, distributed robotics is one of the many approaches to construction automation. Each approach has unique opportunities for allowing for safer, more efficient, and potentially more sustainable construction. And some of these approaches, like as in our cluster, are already being integrated into practice, leading to higher levels of productivity in the building sector. But distributed robotics still needs a decent amount of research to be proven viable. So that's what I hope to be doing together with my colleagues at the NCDC. So in wrapping up, I would just like to thank them, the people who I work with pretty consistently, and thanks for everyone listening here and online as well.
Brilliant, thanks Sam. I've been trying to get Sam to a next build since 2020, and I think we had COVID. Then we had COVID. And then Sam said, oh, I'm redesigning it. Let's do it next year. So these are very different from the machines that I saw those 3 years ago. They kind of look like dustbin lids, beautiful dustbin lids. But these have slimmed down dramatically from Rev 1.
Yeah, definitely.
How heavy are they?
One robot, I think, is 1.5 kilos now.
And obviously you've electrically powered these by wire, but the battery situation?
So we actually, I mean, in most of the videos you see that the robots are wired up. We actually designed it with a battery. The battery lasts for about 6 hours when it's doing kind of these locomotion tasks that I was showing in the presentation. But kind of for ease and in testing these things, we kind of wired them up just because then we don't have to be charging batteries, worrying if it's dead when we want to run some experiments. So
I just kind of imagine IKEA being after you for these to be delivered with every bed or wardrobe to try and put it together. Have you got any questions from Sam? Oh, okay.
I was saying about the wires, they seem to get in the way. I was thinking about Bluetooth technology and then better batteries, like the graphene battery or a biophene battery.
I mean, we're right now using lipos, and it gets us to a certain point. I mean, I think I myself am an architect. I work with one mechanical engineer and one guy who is doing computer science. And so, I mean, our interest is in kind of proving the system, right, to a certain extent. And so therefore, like, the battery is a topic that we try and kind of say, like, we can handle it, but it's not the main topic of our research. Yeah. But thanks for the suggestion.
Is there any plans to use anything other than wood, like aluminium or steel or something?
It's interesting you ask. I mean, I think our intention is to stick with wood here because it has some sort of implication on the larger architectural field, although the first tests that we were doing were with Bosch profiles. Which kind of eases some constraints on the system, right? Because even in milling this groove, we realized that there's like a lot of variation that could happen. So we've come up with some smart ways to deal with that. Like I was talking with the gripper itself, also some like passive mechanisms on the robot, which I didn't really get into so much in this presentation. So it could be, definitely. But right now, I think we're kind of focused on the timber.
Basically, because you've been involved with so much of the research on this, how long before we see robots on construction sites, other than scanning or wandering around doing stuff, to actually positioning, nailing, welding, you name it?
Yeah, I think it's an interesting question. I mean, I think we're getting closer and closer, like you said, like what we see with Spot and some drone technology that for like scanning purposes, especially when we consider these small robots, that they're creeping onto our construction sites in some ways. I don't know how to quantify when like mobile robots might assemble things on construction sites, but I'm hopeful, right? I think like the amount of research is definitely increasing. Like, I mean, Maria will also talk after me, but I think there's more and more research about it, and I think there's some chance that like there's some promising results coming.
Brilliant, thank you. Cheers, Sam. Everyone say thank you to you.